The expansion of the universe is a phenomenon in which the universe continues to grow and galaxies move farther apart over time. The theory dates back to the observations of Edwin Hubble in the early 1900s, who discovered that distant galaxies were becoming redder, meaning that their light was traveling at longer wavelengths. This red shift has been interpreted as a sign that galaxies are moving away from us, leading to the conclusion that the universe itself is expanding. This expansion is the result of the Big Bang that started the universe. In the beginning, all matter and energy was in a warm and dense state. As the universe expanded, it cooled, leading to the formation of atoms, stars, and galaxies. Understanding this expansion is crucial, not only for determining the structure of the universe, but also for determining its age and future trajectory. The rate of expansion is measured by a quantity known as the Hubble constant, which determines how fast galaxies are moving away from each other relative to their distance from us. Cosmic expansion significantly affects our view of the boundaries of the universe. Although we can observe a limited portion of the universe based on the light that has reached us since the Big Bang, the expansion of space also means that there are regions that we will never be able to observe. Because of the expansion, some galaxies are moving away from us at speeds faster than the speed of light, making it impossible for their light to get here even over an infinitely long period of time. It creates a natural limit to the universe we observe, often referred to as the cosmic horizon. In addition, expansion affects the ultimate fate of the universe. Depending on the density and composition of matter and dark energy in space, the universe could continue to expand forever, eventually leading to a cold, dark era, or it could slow down and collapse in a big crash. Understanding cosmic expansion is crucial because it determines not only our current observations, but also predictions about the future of the universe and the very nature of existence. Scientists measure the rate of cosmic expansion using a variety of methods, each of which provides additional insight into the dynamics of the universe. One basic method is to observe distant galaxies and their redshift, a phenomenon in which light from galaxies is stretched to longer wavelengths as they move away from us. By analyzing the degree of redshift, astronomers can determine how fast a galaxy is moving away. This measurement is crucial for calculating the Hubble constant, which determines the relationship between the distance to a galaxy and its recession rate. To obtain accurate distance measurements, astronomers often rely on a class of objects known as standard candles. A well-known example is infrared supernovae, explosions of stars reaching their maximum luminosity. By comparing the brightness of supernovae to their actual brightness, scientists can determine their distance. Combining distance measurements with redshift data will help provide a more complete picture of Hubble's own expansion rate. Another important technique is the measurement of microwave background radiation. For example, the Planck satellite makes very precise measurements of this radiation, showing small changes in temperature throughout the atmosphere. These fluctuations contain information about the early universe and allow scientists to infer its density and overall geometry, providing additional context for determining the rate of expansion. By analyzing the cosmic microwave background, researchers can obtain independent estimates of the Hubble constant. In recent years, controversy has arisen between different measurement methods, indicating that the expansion rate may not be as uniform as previously thought. Although measurements of the cosmic microwave background and observations of local galaxies agree to some extent, the discrepancies indicate that our understanding of cosmic expansion may be missing key details. This ongoing research invites further exploration that could lead to revolutionary discoveries about the composition and evolution of the universe. With these diverse methods, scientists are constantly improving the tools and techniques used to unravel the mysteries of cosmic expansion. Cosmic inflation is a theoretical scheme that assumes an abrupt expansion of the universe that occurred a fraction of a second after the Big Bang. This period of rapid expansion, lasting from about 10 at minus 34 seconds to 10 at minus 32 seconds after onset, implies that the universe increased in size exponentially. During this brief phase, the universe grew from subatomic scales to nearly galaxy size, smoothing out the irregularities and homogeneity of matter over vast distances. The concept of inflation arose to solve some mysteries that the standard Big Bang model could not explain, such as why the universe appears so uniform on large scales despite tiny fluctuations. Inflation assumes that superluminal expansion stretches out all the original irregularities of the universe, leaving a nearly homogeneous state. This theory solves the problem of contraction and explains why the universe is so close to a flat geometry. In addition to defining the universe, inflation is also responsible for the creation of the great structures observed today. During this rapid expansion, variations in the size of the growing universe evolved into the size of the universe, and then into the clusters of galaxies we see today. These differences have been observed in the microwave background radiation and provide strong evidence for the theory of inflation. Globalization has huge implications for our understanding of the early world. It helps explain the initial conditions needed for the Big Bang, and suggests that the universe we observe may be only a small part of a much larger cosmic landscape. This concept opens questions about what may exist beyond our observable universe, and invites exploration of the fundamental dynamics that govern the cosmos. As research in this area continues, inflation remains a powerful tool for understanding the origin and evolution of our universe. Dark energy plays a critical role in shaping the expansion of the universe, acting as a mysterious force to accelerate it. Dark energy, discovered in the late 20th century, is thought to account for about 70% of the total energy content of the universe. Its presence can be inferred from observations of distant supernovae that have been dimmer than expected, indicating that the expansion of the universe is not just happening, but accelerating over time. One of the leading hypotheses to explain dark energy states that it is a constant energy density, uniformly filling space, and exerting a repulsive gravitational force as the universe expands. This formulation is often described by the cosmological constant, a term originally introduced by Albert Einstein in his equations of the general theory of relativity. According to this theory, as the universe grows, the influence of dark energy becomes more pronounced, counteracting the effects of gravity that would otherwise slow the expansion. The acceleration of the universe complicates our understanding of its fate. If dark energy continues to dominate, the universe could expand indefinitely, leading to a scenario known as the Big Freeze. In this case, galaxies disperse, stars burn up, and the universe becomes a cold, dark landscape devoid of active structures. On the other hand, alternative theories suggest that dark energy can vary with time, potentially leading to different scenarios such as collapse or stabilization of the expansion. Current research is focused on trying to understand the true nature of dark energy, including whether it is a fundamental property of space itself or a more dynamic field. Observations from current and future projects, including a survey of large galaxies and improved measurements of the background cosmic microwave radiation, aim to unravel the mysteries of dark energy and its impact on the evolution of the universe. By studying its effects, scientists hope to gain insight into the ultimate fate of the cosmos and refine their models of cosmic expansion. The Big Bang theory is a hypothesis about the ultimate fate of the universe, closely related to the concept of cosmic expansion. According to this scenario, if the acceleration of the universe caused by dark energy continues, it could eventually collapse all structures in the cosmos, from galaxies to atoms. According to this theory, as the universe expands at an ever-increasing rate, The gravitational forces binding galaxies, stars, and even the fundamental forces of nature will be overcome by the repulsive effects of dark energy. In this context, the Great Divide can be understood as the critical point at which the very fabric of space-time becomes so stretched that everything within it separates. As the expansion accelerates, galaxies will first move away from each other at an ever-increasing rate. Eventually, the gravitational forces holding clusters of galaxies together will be destroyed, followed by the disintegration of solar systems and eventually the destruction of planets and all forms of matter. In the final moments of this scenario, even atomic particles could be torn apart, causing the universe to become completely fragmented. The time frame for such an event, according to this theory, could stretch over billions of years. Depending on the nature of dark energy, the Big Rip could occur when the density of dark energy increases over time, creating a situation where the rate of expansion increases uncontrollably. This suggests that the fate of the universe is closely tied to the properties of dark energy. If the gravitational force remains constant or decreases, the Big Rip scenario may not occur, while its increase may lead to its realization. The Big Bang Theory is one of several possible fates for the universe, along with scenarios such as continued expansion leading to a big freeze or collapse in a big crunch. Ongoing observations and research into the behavior of dark energy are crucial to determining which of these scenarios may be more plausible. As scientists deepen their understanding of cosmic expansion and the nature of dark energy, they continue to explore the implications of these theories for the long-term future of the universe. The concept of a multiverse suggests that our universe may be just one of many different universes existing at the same time. This idea stems from various theoretical concepts in cosmology and physics that suggest that different universes may have their own unique physical laws, constants, and even dimensions of space and time. The concept of a multiverse challenges the traditional view of a single, isolated universe, expanding our ideas about reality and existence. There are many theories suggesting the existence of a multiverse. One well-known theory is based on cosmic inflation, which suggests that the rapid expansion of the universe shortly after the Big Bang may have resulted in bubble universes. In this scenario, regions of space inflate at different rates, creating pockets of inflation, each becoming a separate universe. Each bubble has different physical properties, opening up worlds with different rules of behavior. Another approach to the idea of the multiverse comes from the field of quantum mechanics. According to the multiverse interpretation, all the results of the great event would occur in separate, branching worlds. This means that every choice we make or every major decision results in the creation of a new world, and many parallel events occur. The implications of pluralism are profound. This raises fundamental questions about the nature of existence, reality, and our place in it. If there are other universes with different laws of physics, this calls into question the uniqueness of our universe and suggests that the constants we observe may be just one possible set among countless variations. This challenges our understanding of cosmology and physics, as well as our philosophical views of existence and life. While the multiverse remains a tantalizing hypothesis, it poses a serious challenge in terms of empirical verification. There is currently no direct evidence for the existence of other universes, leading to debates in the scientific community about the legitimacy of the multiverse as a scientific theory. As our understanding of the universe and its fundamental physics continues to grow, the study of the universe continues to inspire new research. Researchers have proposed many different theories of the universe, each based on principles of cosmology, quantum mechanics, and theoretical physics. One of the most popular aspects is the increasing number of people in the world. According to this theory, as the universe expands, different regions may collapse at different rates, creating separate bubble worlds. Each bubble may have its own physical properties and rules. This concept not only explains the homogeneity of our own universe, but also allows for the existence of an infinite number of other universes with different properties. Another well-known theory comes from the field of quantum mechanics and is known as the many worlds interpretation. According to this approach, each quantum event, with multiple possible outcomes, results in the creation of a branching universe for each possible outcome. In this interpretation, all potential realities coexist in parallel, so that each choice, event, or dimension gives rise to a separate universe, creating a vast landscape of diverse versions of reality, each reflecting different outcomes of quantum decisions. The third type of multiverse theory has its roots in string theory, specifically in a structure called the landscape multiverse. String theory assumes the existence of multiple dimensions and configurations of matter. Since different solutions to string theory arise from different compactifications of extra dimensions, each configuration can lead to a separate universe with its own set of physical laws, constants, and forces. This landscape approach allows for the existence of a huge number of potential universes governed by different fundamental principles. Another intriguing concept envisions a finite multiverse in which all mathematically possible universes exist. This idea stems from the notion that if mathematical structures exist independently of our universe, then any conceivable universe governed by consistent mathematical laws could also exist. From this perspective, each possible configuration that conforms to logical principles will manifest as a unique universe. Each of these multiverse theories presents a different perspective on the nature of reality and the cosmos. While these concepts provide fascinating explanations and potential ways to reconcile unanswered questions in physics and cosmology, the lack of direct empirical evidence remains a major challenge. Current research aims to further explore these concepts to help determine their viability and implications for our understanding of the cosmos. The bubble universe theory explains the existence of multiple universes using the concept of cosmic inflation, a period of rapid expansion that occurred immediately after the Big Bang. According to this theory, the world experienced an inflationary phase where certain regions of the cosmos grew at different rates. This gave rise to bubbles, each representing a separate world that evolved independently of each other. In the global bubble model, inflation occurs everywhere, but not uniformly. Even if one region of the cosmos does not explode, releasing galaxies and structures, other regions will continue to grow. Each region can become a separate world with its own unique customs, art, and physical laws. Within these bubbles, the processes governing them could be radically different, potentially leading to very different fundamental forces than those observed in our universe. This theory helps solve several cosmological questions. For example, this explains why our universe appears uniform and isotropic on large scales, despite the presence of structures such as galaxies and clusters. Rapid inflation will smooth out any irregularities. The result is a more homogeneous environment inside each bubble after inflation ends. In addition, it allows us to understand why the constants of nature in our universe have certain values, since each bubble may have a different set of values due to the particular dynamics of inflation culminating in that region. Moreover, the bubble universe theory suggests that there could be an infinite number of such bubbles, leading to a multiverse where each bubble could contain life, different types of matter, or even completely different physical laws. This creates a scenario in which realities coexist in a larger cosmic context, fundamentally changing our view of the existence and structure of reality itself. Ultimately, the bubble universe theory serves as a compelling model to explain the diversity of potential universes in a broader framework, expanding our exploration of the cosmos and inviting further inquiry into the nature of space, time, and existence. The many worlds interpretation of quantum mechanics is a theoretical scheme that assumes that all possible outcomes of a quantum event actually occur, each in its own separate branching universe. This interpretation emerged in the mid-20th century, largely due to the work of physicist Hugh Everett III. In large-scale construction methods, particles are in specific positions, demonstrating many aspects at once until observation leads to a solution. However, the many worlds interpretation implies that it is not reducible to a single option, that all possibilities are realized, creating separate and unrelated branches of reality. Consider, for example, a simple quantum experiment in which a particle can move up or down. According to the multiverse interpretation, when a particle is measured, the universe is divided into two parts. In one universe, a particle appears on the surface. In the parallel world, it appears upside down. This bifurcation process continues for all quantum events, resulting in a very complex web of parallel events. Thus, each solution or measurement creates a new world in which all outcomes are possible. This interpretation is closely related to many theories because it assumes the coexistence of many worlds. Each world, in the sense of multiple worlds, presents its own sequence of events, outcomes, and choices. This fits well with concepts such as bubble universe theory, where each bubble can also act as a separate universe, but arises under different conditions rather than as a result of quantum branching. The many worlds interpretation offers elegant solutions to some of the paradoxes of quantum mechanics, such as the observer effect and the collapse of the wave function. However, it remains a subject of controversy among physicists because it challenges our traditional understanding of reality and observations. Critics argue that it lacks direct empirical evidence and raises questions about the nature of measurement and reality itself. Overall, the multiple worlds interpretation enriches the conversation about multiverse theories by suggesting the existence of a vast and diverse set of universes derived from the fundamental principles of quantum mechanics. This connection expands philosophical understanding of the existence and nature of the universe, contributing to a deeper exploration of the implications of quantum mechanics and cosmology. String theory and M-theory offer a fascinating scheme that assumes the existence of multiple universes, expanding our understanding of reality beyond the single universe in which we live. At its core, string theory proposes that the fundamental building blocks of the cosmos are not point particles, but tiny vibrating strings. These strings can oscillate in different ways, leading to a variety of physical phenomena and the types of particles we observe. This model inherently supports the idea of a multiverse, because vibrational patterns can correspond to different physical laws and constants. M-theory is an extension of string theory and shows that these strings exist in higher dimensions. While string theory typically consists of 10 parts, M-theory considers 11 parts. This extra part also allows for interaction with more complex structures, such as the brain. It is a multifaceted entity that can encompass all worlds. Each brain can maintain its own world with a unique set of rules, increasing the possibility of multiple worlds. The mathematics of string theory and M-theory contains solutions that describe a set of discrete worlds called states. These landscapes arise because of the many ways that strings can compact or twist in additional dimensions, creating an incredible variety of possible conditions for different universes. Since different energy states can lead to very different physical realities, it becomes possible to assume that each unique configuration corresponds to a separate universe. Although these theories remain unproven and are still an area of active research, the implications they carry are profound. The landscape of string theory and M-theory not only challenges our preconceived notions of existence, but also opens the door to exploring how universes can interact or be completely isolated from each other. This intriguing possibility forces us to rethink our understanding of space, time, and the very essence of reality. Brain cosmology is a fascinating aspect of string theory and M theory that explores the role of the brain, which is a multidimensional object, in the structure of the universe. In this context, our familiar universe can be envisioned as a three-dimensional brain existing in a higher dimensional space. Just as a piece of paper has two dimensions and can exist within the three-dimensional confines of a room, the brain can exist in additional dimensions that are beyond our current sensory perception. One of the most intriguing implications of brain cosmology is the idea that there could be many other brains, each potentially containing its own universe with separate physical laws. These brains may drift in a wider space, defined by extra dimensions. Thus, different regions of this higher dimensional space may contain entirely separate universes that may have different properties, such as changing constants of nature or alternative forms of matter. Brain collisions offer a particularly exciting explanation for cosmic events such as the Big Bang. When two brains come close enough to each other, their interaction can result in a significant release of energy, resulting in a cosmic explosion that creates a new universe. This model suggests that the Big Bang was not a single event, but rather one of many, suggesting a cyclical process in which brains collide, giving rise to new universes in a cosmic rhythm. Moreover, the dynamics of brain cosmology allow for the possibility of universes branching off from each other. As these brains ebb and flow, they may create different cosmic structures that reflect a diverse tapestry of universes, each of which may experience its own unique evolution. This concept changes our view of existence by expanding the possibilities of our reality to a complex multiverse in which countless parallel and divergent universes may exist, thus expanding the horizons of cosmological research. The concept of extra dimensions in brain theory greatly enriches the discussion of parallel universes by suggesting that what we perceive as a singular reality may be only a thin slice of a much larger cosmic structure. Brain theory envisions our universe as a three-dimensional brain embedded in a higher dimensional space, which may consist of additional spatial dimensions beyond the three we experience on a daily basis. These extra dimensions provide a rich backdrop for a multitude of possibilities, including the existence of multiple parallel universes. The relationship between extra dimensions and parallel universes can be understood through the arrangement and behavior of these brains. Each brain can be thought of as its own universe with unique physical laws and particles. If these brains are in the same higher dimensional space, they may exist side by side, potentially allowing them to interact. However, they may also be separated by large distances in additional dimensions, creating the possibility that these brains, and therefore the universes they support, remain completely isolated from each other. Moreover, the dynamics of these extra dimensions allow for different brain configurations and arrangements. This variability means that different universes can emerge based on the specific properties of each brain and its interactions in higher dimensional space. For example, depending on how a brain is formed or positioned in relation to other brains, the universe may have a different set of fundamental constants or forces, resulting in divergent realities. The interaction of additional dimensions and brain configurations implies a vast landscape of potential universes, where any slight change in the parameters governing the brain could lead to the creation of an entirely new universe. This scheme not only introduces the concept of parallel universes existing side by side, but also invites us to speculate about possible connections and divergences between them, hinting at a rich and complex multiverse waiting to be explored. The ekpyrotic model of the universe is an alternative view of the origin of the universe, departing from the traditional Big Bang theory. This model suggests that our universe arose from the collision of two three-dimensional brains in higher dimensional space. Within the outfit, the universe undergoes an evolutionary process involving cyclical events in which brains collide, creating energy and leading to the formation of new cosmic structures rather than having a single explosive origin. Unlike the Big Bang theory, which describes the universe as expanding from an infinitely dense point about 13.8 billion years ago, the ekpyrotic model suggests that the universe has existed eternally and cyclically. What this means is that there will be a series of brain collisions, generating many Big Bangs over an infinite amount of time. Each collision triggers a new era of expansion followed by subsequent contractions, suggesting a continuous cycle of creation and destruction rather than a single explosive event. One key difference is how each model explains the homogeneity and large-scale structure of the universe. Big Bang theory relies on an inflationary phase to explain observations such as the cosmic microwave background radiation and the uniform distribution of galaxies. On the other hand, the ekpyrotic universe attributes these features to the interaction and dynamics of colliding brains. Such an interaction allows for multiple outcomes, keeping the cosmic background constant and not requiring rapid inflationary expansion. In addition, the ekpyrotic model allows us to explore additional dimensions and the nature of the space-time continuum in a way that the Big Bang theory does not. The ekpyrotic approach, which combines the concepts of string theory and higher dimensional spaces, opens up new possibilities for understanding the fundamental fabric of reality, challenging our notion of time and existence itself. In her view, the universe is not simply the consequence of a single event, but part of a continuous cycle of cosmic transformations. Collisions between brains are the central mechanism for the creation of new universes within the brain cosmology. When two three-dimensional brains approach each other in higher dimensional space, they can engage in a powerful interaction. This interaction is akin to the collision of two massive objects, in which the energy released can be enormous and lead to a cosmic event that can give rise to a new universe. During such a collision, energy concentrated in the brain could trigger a significant event similar to what we understand as the Big Bang. It is here that the ekpyrotic model sheds light on the nature of these cosmic births. When brains collide, they can release vast amounts of energy, inflating a region of space and creating the fundamental particles and forces that will define the newly formed universe. This process forms the fundamental elements of our cosmos, leading to the expansion and evolution of that universe into a separate reality. In this scenario, each brain collision gives rise to a separate universe with its own unique physical laws and properties. The specifics of these laws depend on the characteristics of the brains involved, including their energy levels and the configuration of their interactions in additional dimensions. Thus, varying the conditions during each collision can lead to a rich variety of universes, each with the potential for different types of matter and fundamental forces. Moreover, this model supports a cyclical view of the existence of the universe. As brains continue to move and collide from time to time, the formation of new universes may become a recurring phenomenon, suggesting that what we perceive as our universe today may be one of countless others that have emerged from similar interactions over cosmic time. This continuous cycle takes us away from a single point of reference. This paints a picture of a dynamic multiverse constantly giving birth to new realities through the energetic dance of brains in higher dimensions. Observational evidence in favor of brain cosmology remains largely indirect, as the concepts and characteristics associated with this model are difficult to test with current technologies and techniques. However, some features of the universe observed in cosmological studies contain intriguing hints that may support brain cosmology and related theories. One important area of research is the cosmic microwave background radiation, which represents a remnant of the hot and dense state of the early universe. The regularities and fluctuations of this radiation help cosmologists understand the formation and evolution of the universe. Although the standard model of cosmology adequately explains these observations using inflationary theory, some researchers have argued that unique signatures arising from brain interactions, such as potential effects of brain collisions, may also be evident in the cosmic microwave background. Features such as variations in temperature or polarization may arise from unique dynamics introduced by brain interactions. Another aspect is related to the distribution of large-scale structures in the universe, such as galaxies and galaxy clusters. Brain cosmology suggests that these structures may form differently as a result of brain dynamics and interactions in higher dimensions. Recent studies mapping the distribution of matter in the universe may provide insight into whether these features are consistent with predictions of brain cosmology, suggesting the need for deeper analysis and testing of more specific models against observational data. Gravitational waves could also be a source of evidence for brain cosmology. Collisions between brains can create ripples in space-time that can be detected as gravitational waves. If scientists are able to detect signatures or patterns in gravitational waves that correlate with collision events in the brain, it could bolster the theory. While brain cosmology still needs a solid observational foundation, advances in technology and cosmological research may one day reveal more precise evidence. Exploring the structure of the universe continues to challenge and inspire scientists to take new approaches, emphasizing the evolutionary nature of our understanding. As we look deeper into space, the subtle signs of brain-to-brain interactions may eventually come into sharper focus, potentially changing our view of the universe itself.